So from today on, pretty much for the rest of the course until the course ends, what we're going to be discussing is waves in magnetohydrodynamics, which by now we abbreviate as MHD, as you know, right? So why talk about waves? We have already talked about sound waves, of course, in fluid dynamics, and we will briefly review that right now. But the whole point of magnetohydrodynamics is that it's hydrodynamics plus a magnetic field, isn't it? And we've seen all kinds of curious aspects of magnetic fields. We've seen that magnetic fields act like rubber bands and so on and so forth. So simply from the fact that, as we have noted earlier, magnetic fields, the presence of a magnetic field, presence of B makes the pressure anisotropic, right? In other words, the pressure tensor, the components of the pressure along the magnetic field and perpendicular to the magnetic field are different, right? So you would imagine that things would be different in the presence of a magnetic field, right? The kinds of waves that can be supported by a medium containing a magnetic field will be different, right? That is why we are starting to examine the phenomenon of waves in MHD. As it happens, there are three types of waves. One of them is the usual sound waves in hydrodynamics, which we've already encountered, but we will discuss it very briefly just for the sake of completeness. I will hurry over it because we've already discussed it, but it's good to discuss it right before the other kinds of waves. You will see that there's certain amount of completeness that's accrued by a discussion, right? So the first one is the usual sound wave in hydrodynamics. The other two, which are actually technically other three. Technically three. I call this two, but one of them is the Alfven wave, and the other one I call magnetosonic, but actually there are two kinds of magnetosonic waves. Okay, so really there are three more waves in addition to the sound wave, and so the waves other than the sound waves are essentially hybrids between the sound speed and what's called the Alfven speed. These are what are called magnetosonic waves. Okay, these are hybrids between the Alfven speed and the sound speed. Okay, so we will discuss these three kinds of waves as we go along. The Alfven speed, on the other hand, the Alfven wave, on the other hand, arises exclusively from the presence of a magnetic field. It's a transverse wave, much like the kind of waves that would be excited on a string, on a stretched string, like a guitar string, for instance. And you immediately see the analogy, right? We talked about magnetic fields as rubber bands of sorts, strings of sorts. So these kinds of rubber bands, you can imagine that they will support transverse waves. You take a rubber band, you stretch it, and you twang it in a transverse manner, and there will be waves that will propagate along that, and those are exactly what Alfven waves are. Okay, right. So to begin with, let us quickly review the sound wave, and so that's what we will do for the remainder of this particular session. Right. So you've already seen this. We have the mass continuity equation written in the Eulerian form and the momentum continuity equation. We will not bother about viscosity for the time being. This is only for inviscid flows, which is the Euler equation, right? So this is the momentum continuity equation for inviscid flows, and that's a mass continuity equation. And what we are now going to do is we are going to perturb the background, right? So let us consider a uniform static background characterized by some background density rho naught, some background pressure u naught, and without loss of generality, we can consider background velocity u naught to be equal to 0, right? No background velocity, no breeze flowing through the room. The air in this room is static. Okay. Now what we're going to do, if you remember, we are going to perturb this background. We are going to the perturbations will be denoted by subscripts 1, rho 1, p1 and some sort of a perturbed velocity, which is obviously non-zero. Okay, and you remember the main thing, so the total density would be the background density plus the perturbed density. So this is background, right, and this is the perturbation, right. So similarly, the total pressure would be the background pressure plus the perturbed pressure, so on and so forth. And the total velocity is simply the perturbed velocity, because the background velocity was taken to be 0 without loss of generality. The other thing, of course, is that the perturbations are small. In other words, rho 1 is much smaller than rho naught, p1 is much smaller than p naught, and so on and so forth. And u1 is just small, the background was exactly equal to 0, so there's nothing to compare u1 with. Okay, so it's simply small. Now what we do is we substitute these total quantities, the background plus the perturbations, in the mass conservation equation, right, in this equation right here. Okay, and recognize that since the background is taken to be uniform and static, we recognize the space and time derivative. So static means the time derivatives of all quantities with subscript 0 becomes 0, right, and the space derivatives, in other words d over dx of rho naught or d over dx of p naught, would be 0. That's because the background is uniform. So the background is uniform and static, right. So that's what, so you substitute rho equals rho naught plus rho 1. Anywhere you see a d rho naught dt, you set that equal to 0. Anywhere you see a d rho naught over dx, you set that equal to 0, so on and so forth, right. And so after you do that, this is what becomes of the mass continuity equation. I'm going a little fast because we've already seen this before. Okay, I'm simply redoing sound waves very quickly for the sake of completeness. So this is the perturbed mass continuity equation. What's more, since the perturbations are taken to be small, products of small quantities, rho 1 times something of the dimensions of u1, it's actually divergence of u1, but that's okay, it involves u1. Okay, so it's like 0.1 times 0.1 is 0.01. So products of small quantities can be neglected. So when you expand this, this becomes rho naught divergence of u1 plus rho 1 divergence of u1, right. So the rho 1 times divergence of u1 is neglected in favor of the first quantity, right. So this is the linearized, so this is what's called the linearized mass continuity equation, this one. Okay, similarly one can write down a linearized momentum equation, right. Similarly, substituting in the momentum equation using the same things. So wherever you see d rho naught dt or d rho naught dx, you neglect it, and obviously quantities like this are negligible, because this involves products of small quantities, right, u1 times gradient of u1. So you neglect this. So this is entirely neglected. So similarly, rho 1 times du1 dt, although it's a derivative, it's still product of small quantity, so that's neglected. So you are left with this very simple equation, which is the linearized momentum equation. So this is the linearized momentum equation, this one. Okay, so you have this. Alternatively, instead of using the pressure, we can write it in terms of the gradient of the perturbed density, okay, gradient of rho 1, and we have to make use of the chain rule, of course, and this quantity is the sound speed, as we know, right. And so You combine the linearized mass continuity equation and the momentum continuity equation to obtain a second order wave equation for the density perturbations. We've seen this before. This is the speed of sound. So, this guy which appears, so this is a wave equation, and whatever appears here is the speed of the wave, and this is the speed of sound. So, by definition, simply by virtue of writing down this equation, we can identify C sub s as the speed at which small density, or for that matter velocity, you can obtain an equation that looks exactly like this for the quantity u1. Okay. So, C sub s is the speed at which small density or velocity perturbations travel, and it's the speed of sound. And we also Fourier analyzed the equation. In other words, what we do is we instead of a d over dt, we can write an e raised to I omega t. Instead of a d over dx, we can write an e raised to I k, right. So, you linearize these two equations, and that's what it looks like. The only reason I'm doing this is to get the important dispersion relation. So, this is the dispersion relation, okay, the omega k relation. And what's evident from this dispersion relation is just the main thing is that sound waves are non-dispersive. The omega over k is the same no matter what the omega is. Okay, it's not like light passing through a prism where different wavelengths have different velocities. Okay, all wavelengths have the same velocity. For that matter, even d omega dk, which is the group velocity, is the same. So, this is the other thing. Sound waves are non-dispersive. In other words, low frequencies, high frequencies, they all travel at the same velocity, and sound waves are a consequence of compressibility, and in a given medium characterized by a given background density, pressure and temperature, it represents the characteristic speed at which small disturbances propagate. Very, very important. Okay, there is only one speed at which small disturbances can propagate. I mean, given a certain temperature in the room, or given a certain background density and pressure, okay, which is the same thing as saying temperature. And because if you take an equation of state, these three quantities are related to each other, right. So, given a certain temperature, there is only one speed at which small perturbations can propagate, small unmagnetized perturbations can propagate, and so put it another way, it's a characteristic speed for small perturbations in a given medium. Okay, and the actual speed of perturbations can depend upon the manner in which this is a spelling mistake. It should be polytropic. I beg your pardon for that. Okay, it's not ploitropic, it's polytropic. So, essentially what this is saying is, depending upon the thermodynamics of these perturbations, okay, these perturbations can be adiabatic or isothermal, right, or something in between. So, the thermodynamics of these perturbations is all hidden, is all contained in this gamma parameter. So, depending upon the thermodynamics of these perturbations, the sound speed can be different. Okay. So, it's the speed at which physical information propagates via pressure disturbances. The speed of sound is thus linked to the concept of physical causality, in that you cannot hear what I am speaking until the sound waves have had time to reach from me to you. Okay. And as we have seen, depending upon whether an object is subsonic or supersonic or something, the dynamics will be very, very different. Okay. Now, imagine now how much more complicated. So, essentially the point, the real reason I wanted to do this recap right now is to emphasize once again the fact that the sound speed is a characteristic speed. Okay. Now, owing to the presence of the magnetic field, okay, there can be other characteristic speeds as well. In fact, to be precise, 3 more characteristic speeds: the Alfven speed, the fast magnetosonic speed, and the slow magnetosonic speed. The magnetosonic speeds, as the name implies, are mixtures between the Alfven mode of propagation and the regular sound propagation that we've seen right now. So, now imagine now you have 4 characteristic speeds. So now this really makes the dynamics of a magnetized fluids very, very interesting and very, very rich. Okay. We have already seen that depending upon whether the speed at which an object or the fluid is flowing, depending upon whether it's subsonic or supersonic, the dynamics are very different. Now just imagine you've got 3 more characteristic speeds. Okay. So depending upon whether or not the flow speed or object speed is below or above any one of these characteristic speeds, the dynamics will be different now. Okay. So this is just to give you a hint of how interesting things can become. Okay. So now let us start to discuss one of the most important modes in magnetohydrodynamics, that of the Alfven mode. Okay. So for simplicity and without loss of generality, let's consider that the magnetic field is exclusively in the magnetic field only in the z direction. That's what this is saying, right? And if I have any other direction, that's okay, right? I mean, I can always superpose my solutions. So that's why I say without loss of generality. Okay. So from now onwards, I consider the magnetic field to be only in the z direction. Okay. The x and y directions are orthogonal to z, obviously, and for concreteness, we take everything to be uniform along y. In other words, all derivatives with respect to y are 0, e.g. d rho dy, dp dy, these are all equal to 0. Okay. So the medium is completely uniform along y. Okay. And x is the only orthogonal direction. Again, this is completely without loss of generality. If you have variations along y, we can next consider everything to be uniform along the x direction and consider variations along the y direction and superpose these two solutions together. Linear superposition. Okay. So this does not in any way take away the generality of what we are discussing. It just simplifies the math, which we definitely want to do. As you'll see, the math does get a little hairy. Okay. Right. As before, now this is what we call, as before, we consider the background density plus a perturbation in density. So this is the perturbation. This would be density perturbation. This is what we used to call, rho subscript 1 earlier. Now we're calling it delta rho. It's the same thing, right? Density perturbation. And this is the pressure perturbation. Okay, right. So now, and in addition to pressure and density, of course, you have the magnetic field, isn't it? So I perturb the magnetic field as well with a delta B. Okay, and whatever velocities there are, the background velocity was 0, and so whatever velocities there are the perturbed velocities, and therefore V is small. As before, the perturbed quantities are all small in comparison to the background quantities. In other words, delta rho is very, very small in comparison to rho, delta P is very, very small in comparison to P, and delta B is very small in comparison to B. Okay, right. Now, as before, we will not repeat the linearized continuity equation, the mass continuity equation. It looks like this. It's exactly the same as what we've derived. There's the reason I just recapitulated, the regular sound wave a little earlier. So the linearized continuity equation is this. The linearized momentum equation, now you remember we only had this chunk and this chunk in the momentum equation, right? These two chunks were the only ones that were there, and this now is addition due to the fact that there is a Lorentz force. Okay, so this is an all important addition to the momentum equation. Okay, well, in fact, this is an all important addition, period. As far as Alfven waves are concerned, the linearized continuity equation is exactly the same as what used to be there for sound waves. The only new thing is this. Okay, and compared with the linearized equation of motion for plane hydrodynamics, as we just said, this is the new chunk. This is the only new term. Okay, and I've simply written it down. I urge you to look at the J cross B. Now, essentially it arises, this whole thing arises from linearizing J cross B, where J is nothing but curl of B, isn't it? And in place of B, you write B plus delta B. That's what you do, right? So, and you do the usual thing, you neglect the space and time derivatives of the background, and you neglect products of small quantities. Once you do that, you will arrive at this extra chunk. Okay, so which is why I'm saying convince yourself. This is very, very important. I have not given you the steps. The steps are the philosophy of arriving at the steps is exactly the same as what was done for the sound waves. And so yeah, so this is the only new term now. And of course, when you're talking MHD, you cannot escape the induction equation, the all important induction equation. So the linearized induction equation, again, linearizing any equation, the same philosophy, neglect, take the background to be spatial, uniform in space and time, and neglect products of small quantities. That's all. So the linearized induction equation is now this, right? V is already small. V is a delta like quantity already. Okay, right. So that's it. You have these three equations, the ones shown in blue. These are the three equations that we have to work with. And the one thing to do is these are vectors, right? V is a vector, right? So what we do is you split the equations of motion and induction into components. No need to worry about this. Just this and this, you split it into components. You split it into x, y, and z components. Okay, and it looks a little hairy, but this is all. I mean, it's all quite straightforward. Okay, all this is splitting up the equation of motion and induction into components. Okay, so you have this, and this. So it's all quite straightforward. Somewhat lengthy, but straightforward, which is what I want to emphasize. Okay, so these equations are nothing but this guy and this guy written down in component form. That is all. Okay, now the thing to realize, there's a reason I marked this and this in red. Okay, the reason is you can see that the equations marked in red are the y components of the velocity and magnetic field, and they are not coupled with the other components. You see, you have Vy, you have delta By, Vy. There is no appearance of a Vz or a Vx or Bz or Bx anywhere here. Okay, therefore, if you can, it's perfectly acceptable to set Vx, Vz, delta Bx, delta Bz, and delta P and delta rho all equal to 0. Okay, in other words, no perturbations, no perturbed velocities in the x or z direction, no perturbed magnetic fields in the x and z direction. In fact, no perturbations of pressure or density either. And still expect a non-trivial solution from these two equations. Why is that? They only concern each other. They only talk to each other. Okay, delta Vy and delta By. So Vy, which is the same as delta Vy because V is small, Vy and delta By only talk to each other. They don't care about the rest of them. The rest of the components might as well be simply set to 0, which is what we'll do in a minute. And so you just set all of these to 0, which is to say I just neglect the other equations written in black. I only look at these two equations, right? And these are coupled first order equations. And what does one normally do? With coupled first order equations, you try to see if there's a way that you can combine them into one second order equation, right? You see you have a dvy dt and you have a dvy dz. So suppose I took time derivative of this entire equation. Yeah. So I would have a d square delta by dt square equals b times d over dz of dvy dt, and in place of dvy dt I substitute this, right. So alternatively you could write down this system of equations as something like this, where theta is essentially just the angle. Theta is just simply, theta is the angle with respect to z, okay, which is where the sine theta and cosine theta come from. But anyhow, don't worry about it. This is all I want to say is this is an equivalent way of writing this system of equations. And here too you can see that the equation for Vy is decoupled from the other ones, all right, and there is an appearance of the C sub s, which is the sound speed, and the appearance of a Va, which we will see what it is. All I want to say is this is an alternative way of writing down this. If you wish, you can skip this entire slide, don't worry about it. You can convince yourself about it later on. So simply moving on from the two red equations, okay, the two coupled first order differential equations, and so you combine them into a second order equation like this, okay, you get this, all right. What this is saying is that when I say delta by comma Vy, what this is saying is that it's the same equation for delta by as well as Vy. In other words, d square over dt square delta by minus some speed, okay, d squared over dz squared delta by is equal to 0. And same thing, instead of delta by you can substitute Vy and you will get the same equation, where this all important Va squared is b squared over 4 pi, this thing. This is the wave speed. Okay. Now having done this, it's important to sort of see what kind of wave this is. Okay, this is very, very important. We will talk about these 2 points, but the other, the most important point that I want to emphasize right now is that this involves only k sub z, only a d square over dz squared. In other words, the waves propagate along the magnetic field. Remember, the magnetic field is pointing along the z direction, and this propagation is only involves a d square over dz squared. In other words, the propagation vector only has a k sub z. Okay, so the waves propagate along the magnetic field. That's one thing. The other thing is that you see this, the delta B and the V have only y components, and the y we know is orthogonal to z, right? That's why, so the delta B, the magnetic field perturbations and the velocity perturbations are perpendicular to the wave propagation vector as well as the magnetic field, much like waves on a string, transverse waves on a string, to be precise. It's exactly like that. You have a string and you twang it like so. You have a string like this, and you give it little velocity perturbations like this. Yeah. So the perturbations are transverse to the direction of the string, and these perturbations also propagate along the string like so. Okay. So these Alfven waves are exactly analogous to transverse waves on a string, and when we meet next, we will take up this the properties, the other properties of the Alfven wave in a little more detail. Thank you. That's it for now.